Hello everyone, my name is Aybora and today I will present our research paper titled as Improved Hard Example Mining Approach for Single-Shot Object Detectors. This study is done in Center for Image Analysis of Middle East Technical University and it is funded by ASELSAN Inc. Before I start, please have a look at my outline. Well, the main aims of this study are observing the performance of two existing hard example mining approaches within a state-of-the-art object detector and adapting, improving and combining these methods to increase the detection performance. After the utilization of the CNNs on discriminative problems, we see a performance increase on the image classification and object detection. And we know that the recent object detectors work fine on perfectly balanced datasets such as MS-COCO or Pascal VOC. On the other hand, the real problem is on datasets where the background and foreground is imbalanced, especially on the small targets. This causes a tail problem. As you can see in this example image, the target is a small UAV and its 20 pixel height is so small with respect to the whole image. So there's a huge size difference between the foreground and the background of the targets. In literature, there are different types of solutions for imbalanced data. One of them is manipulating the loss function. So in this work, we focused on that. We have used two existing approaches. One of them is focal loss and the other is loss rank mining. Then we have combined these approaches and improved them. Combined method is applied into state-of-the-art object detector YOLO V5. Our proposed unsupervised performance evaluation methods shows a performance improvement on hard examples. So how we do that? Let me explain our method. First of all, we proposed balanced focal loss. In overall loss function of YOLO V5, there is an objectness loss, bounding box regression loss, and class loss. We are focused on the objectness loss. Originally, for objectness loss, popular cross-entropy function is used. In RetinaNet, the authors have proposed focal loss with gamma parameter. Here is the original focal objectness loss function. The 1 minus p term is always between 0 and 1. When a gamma parameter is bigger than 1 is selected, the loss value becomes exponentially smaller and it makes objectness loss term relatively smaller than the bounding box and class losses. Since same learning rate is used for all losses, objectness loss becomes ineffective. Our solution is a correction term, or in our definition, a balancing term. We try to multiply the loss function with some number bigger than 1 to make objectness loss term comparable with the other losses. The other approach we have implemented is loss rank mining. This is originally proposed for YOLO V2, which uses only one feature map. Our proposed method modifies loss rank mining for YOLO V5, which has 3 feature maps for small, medium, and large objects. But what is loss rank mining? In LRM, simply cells with the highest loss values are selected for backpropagation. Top B percentage of cells are selected and rest of them are omitted. Let me cover this part with more detail in this figure. At the left, you can see original YOLO V5 objectness loss function. For each cell, binary cross entropy is calculated, mean of them is taken, and sum of the losses of 3 feature maps gives us a final objectness loss value. In our proposed method, on the other hand, firstly, balanced focal loss is applied for each cell. These loss values are firstly flattened for each image and then sorted. Highest B proportion of cells for each image is selected and the rest of them are omitted. Then we take the mean of the cells and the sum gives us the final objectness loss. So up to now we have covered the introduction and proposed methods. Now I will go on with the experiments. In the experiments, 2021 Anti-UAV Challenge Dataset is used. For an ablation study, we have compared the methods head-to-head with an unsupervised way. We don't know samples are hard examples or not, so we have made an assumption. Firstly, the detections are classified as true positive, true negative, false positive, and false negative according to 0.5 IOU threshold. In head-to-head comparison, for example, if first method gives a false positive, meanwhile second method shows a true negative for the same cell, then we assume that that cell is a hard example and second method works better on that cell. We have done this for the whole set and for the pairs true positive, true positive, true positive, false negative, true negative, false positive, false positive, false positive, and finally false negative, false negative. And here are some of our results. In these tables, first two rows shows the percentage of the frames where the second method is better, and the second two rows shows the frames where first method is better. Table 1 compares original loss, original YOLO v5 and original focal loss function. As you can see, original YOLO v5 cross entropy loss works better than original focal loss by 6% due to the reasons I have tried to explain before. On the other hand, when we have used balanced focal loss, as in table 2, the performance of YOLO v5 increases by 3% with respect to original cross entropy loss. Here is the comparison of the original YOLO v5 cross entropy with loss rank mining method. In table 3, where we can see a performance increase of 4.5% with LRM. And when we combine the two methods, balanced focal loss and loss rank mining as in table 4, this increase goes further, around 5.5 in this matrix with respect to the original YOLO v5 cross entropy function. To compare the methods in popular object detection metrics, here are some final results with precision, recall, and map scores. These scores are also verifies our ablation studies by increasing the map 0.5 score by more than 3%. So in conclusion, in this work, two existing hard example mining approaches are modified and adapted for a state-of-the-art object detector YOLO v5. While original focal loss degrades precision, balanced focal loss increases the overall performance. Balanced focal loss and LRM is combined as proposed loss function with 93.5% map score, which is higher than the baseline score by 3.1. So thank you for listening. Have a nice day.